Hello, friends. This is a replacement lecture for the lecture on Wednesday. I did some things that were a little bit confusing, but I think the thing that I most regret was I really beat myself up for screwing up. And part of it is just, being embarrassed, like a whole ego thing. I'm the guy who's supposed to know everything. And then kind of made a couple slip ups in an example, and I think that it really wasn't as good as it was, but could have good as it could have been. But the worst thing I did was to sit there and rip on myself for making a mistake. So apologies for that. Generally, I want you all to treat yourself with compassion, in particular when you're doing math. That's one of the problems in this world that math has, is people have bad experiences early on, and then that trauma just keeps repeating over and over again, and you tell yourself you're dumb and you can't do it. I don't think anybody in this class, is hopefully suffering from that. You're all STEM folk, but it happens to the best of us, I guess. Not that I'm the best of us. I'm just the oldest and the one who knows the most math. Um, but it happened to me. And like I said, part of that is just being on the stage. Normally in my private work, I don't get frustrated. Um, but embarrassment can do things to our minds. So anyway, this lecture is about systems of equations, of differential equations. And what we're going to be looking at are things that look very similar to other things we've seen this semester, except we're going to have a couple of variables floating around. You've already seen examples of these in class. I showed you the mass spring system and then the love affair example. And we'll see a couple more examples before this is all done. In particular, some predator prey models and competing species models, which are used, or even still used, even though math is old, and this math is old, in biology, and probably some other places too, but I know mostly biology. So what we're going to have is this system of two equations and two unknowns, x and y. This x dot is you could think of this as the horizontal velocity or the horizontal rate of change. So let me get that horizontal rate of change. And then this y dot is the vertical rate of change. And let me clear that up there, get that out of the way. Notice that we have a dot here, so that x dot is dx dt. It's the derivative of x with respect to time. And no t appears in this equation beyond that denominator in the differential. So these are called autonomous, and that's really the only kind we will deal with, is autonomous systems of differential equations. And we're only going to deal with two variables. This can be done with any number of variables. So what we've got is an x and a y, and this gives us a plane. And in fact, we call this the phase plane. And it's just going to represent the state of the system at a particular time. So what does this all mean? How do I put this together and make sense of it? Well, you've got some particular point, x naught, y naught, in the plane, like so. And you can use this system to get the components, the horizontal and vertical components of a direction vector in which we would head from here. So for this one, x dot, the horizontal rate of change, is whatever that function is on the right, evaluated at the point. And y dot is the same for that potentially and probably different function to determine the vertical rate of change. So you plug the point into this right-hand side, and then you come down to the graph, and you make a little vector that, and if you're doing this by hand, it's going to be very rough. This horizontal distance will represent the magnitude of dx dt, so that's my x dot, whatever number comes out there, and whatever number comes out for y dot, I'm going to make that vertical part that high. If x dot is positive, that is a rightward movement. If x dot is negative, that's a leftward movement. If y dot is positive, that's up. And if y dot is negative, that's down. And so we've got all the cardinal directions covered. And then we make a vector that has those components. And that's our velocity vector. We do this at every single point in the plane, and we start to get a sense of a flow in the plane. I'm going to make a very simple one here, and the flow is just these vectors are all parallel and up and to the right. A solution to this system would be a trajectory, so a path that was consistent with these. And these arrows are the tangent vectors to the solution. So if I started right here on this one, red dot, that's my initial condition. It would say go up and to the right, and it kind of looks like I would just keep on cruising up and to the right. And there, see, it made a fancy line for me that actually doesn't look right anymore. So the computer didn't help me too much there. But all the trajectories here seem like they would look like straight lines moving to the right. Remember, time. Well, you can actually flow left and right in here. So since time doesn't show up, we don't have a time axis, and that's something you'll have to get used to. This is analogous to the phase lines that we did when we had things like x dot equals x times 1 minus x. A very similar process here, but gets way more complicated. And if you were there in class on Wednesday, you saw me get myself all gunked up over this. So let's clear some things up and look at an example. So here, I'm just going to start off. I'm really just going to start off with the example that I kind of barfed in class, which was the last example. And this was x minus y. Now, this system, notice that the x dot depends on x and y, and similarly for the y dot. This is called a coupled system because the x dot system depends on something besides x, and similarly for the y dot. An uncoupled system would just have x dot equals a pure function of x and y dot equals a pure function of y. So we've got a coupled system here, and that's when things get pretty interesting. Now the process is as follows. Instead of just going to the plane and just plunking out arrow after arrow, making a grid of arrows and then kind of guessing on it, we are going to have a process that helps us get the skeleton for the flow. So let me make an axis here. And step one is to sketch the nullclines in the plane. Now, a nullcline is a curve in the plane. It may be a line, might be a parabola, it can be lots of different shapes where x dot equals 0. And then there's another one. So there's two nullclines for these problems we're going to have. And then I'm going to figure out where y dot equals 0. So x dot equals 0 when x plus y equals 0. And that is going to happen when y equals negative x, all along that diagonal line there. And for the y dot equals 0, I'm just looking for a different color here. We've got the equation is x minus y for y dot, so I get x minus y must equal 0 if y dot equals 0. And that happens when y equals x, so the other diagonal over here. And I'm trying to make those dotted because if I make them solid, we might get confused. Perhaps the royal I might get confused. We might get confused and think they are trajectories. So that's step one, sketch the null lines. The place anywhere where the null lines intersect is going to be an equilibrium solution. So find the equilibrium solutions is the step two. You got to have some kind of action to take there. That's just the intersection of these null lines. It's where simultaneously x dot is equal to 0 and y dot is equal to 0. Intersections, because there can be more than one. And that means our equilibrium solution here is 0, 0. That's the only equilibrium. So if you start at 0, 0, if your initial conditions are 0, 0, x dot is 0 and y dot is 0 forever, you're not moving. You're stuck right there. Now you can never enter or leave an equilibrium solution no matter what. And I'm going to reiterate this point a couple of times. When I have a solution curve, it can't intersect any other solution curve. For the kinds of problems we're going to have, we have uniqueness of solutions. So that means if the two cannot intersect, so you'll never have a crossing of trajectories, and you'll certainly never enter or leave in equilibrium, be it stable or unstable. And yeah, and maybe half stable or something weirder than that. We're going to have all that stuff coming in. So those are the first two steps, and we've got that all sketched out. And I'm going to stick on this page because, and you can stop this video if you need to check out what's there. But I want to just keep my graph. I don't want to have to remake that dang graph every time. So step 3 is going to be to test the sign of x dot and y dot in the regions between null lines. So one thing to keep in mind to help you manage this process is that each null line represents x dot equaling 0 or y dot equaling 0. So this one here is where x dot equals 0, and this other one is where y dot equals 0. That means if I just think about the plane with that green x dot equals 0 null line, on one side of it x dot is positive, and on the other side x dot is negative. Or actually, it could possibly be positive. So in other words, I just need to test on the sides of each null line. So what do I mean by this? Let's take a point out here. So I'm taking the point 1, 0 in the plane, and I'm going to plug that into my system, and I'm going to get x dot equals 1 plus 0, and I'm going to get y dot equals 1 minus 0, which is 1. And that means at that point, x dot is positive. So let's kind of just summarize that here. So x dot is positive and y dot is positive. And I can do this in each region. So for example, if I test, and probably should, unless I get a lot of experience with this, for example, I can look at this, and maybe you can too, and see that once I know x dot is positive on one side, it's got to be negative on the other. Now, again, that's not always true, but it's probably going to be true for most of the stuff we do. So over here at the point 0, 1, I get x dot equals 0 plus 1, which is 1, and y dot equals 0 minus 1, which is minus 1. So now check that out. That was the y dot equals 0 null cline. And on the other side of it, let me get a different color here. Let me get red. So over here, we've got x dot is positive and y dot is negative. And then down here, we had x dot was positive and y dot was positive. Notice that x dot did not change sign, but y dot did as we crossed over the y dot null cline. And you could go ahead and test other points in here. I always go for the lowest hanging fruit, and you should test those 2 points out. But what you're going to find, and let me do this in red, is that over here we're going to have x dot is negative. And let's see, what side of the y-cline are we on? We're on the y less than 0 side. So, and y is negative here. Y dot is negative. And then down in this final little triangular piece that frames the lower y-axis, we're going to have x dot is negative, and we're going to have y dot is positive. So I recommend going through this, making these things, writing on your plot, maybe making a scratch plot, because here I'm going to have the luxury of erasing some things that I have room. So you might want to do a separate piece of analysis before you make your final graph. And I will be giving a homework assignment in this lecture, and we'll see if we can shoot for next Wednesday, but we'll see how it goes. Okay, cool. So now I know all those things. So check this out. On the upper right half of the green diagonal, on the upper right half of that, I have x dot is positive. So that means all along the y dot null cline, I have a horizontal change to the right. I have a positive x dot. Remember, y dot equals 0 on this null cline. That means there's no vertical component. Now these vectors would actually get bigger and or longer as I got further out, and I'm not worrying about that too much. On the other side of that blue diagonal, I have x dot is negative. So on the whole lower left side of that green diagonal, we have purely horizontal change to the left. Now let's go to the green null cline and get some direction vectors there. Notice that on the x dot null cline, we have a purely vertical change. There's no horizontal component to our vectors, so they're either up or down. And they are going to be up because I see that y dot is positive down here. So I'm just going to put upward vectors here. And then over here, I'm going to get y dot is negative, and make sure you see that these arrows, make sure you understand why those arrows up there point straight down. It's because y dot is negative in that whole upper left part that's split by y dot equals 0 blue dash line. All right, so now we're starting to get some idea of what's going on here. And I just want to make an observation if we're thinking about flow. Look in that upper left, excuse me, that upper top triangle that frames the positive y-axis. All the flow is out of that region. So you can think of that as just like it's just expelling things. Anything that starts in that region will eventually leave that region. All routes head out. Similarly for the one in the lower part of the graph. You see that there's flow to the left on the blue line and up on the green line. So if you're in that lower region, you're leaving it at some point. However, once you're in the left or the right region, you're going to stay in that region. There's no way to escape it. And you got a lot of space, right? So it's a big triangle on either side. But just a thing to note, and when you start thinking about this as flows of current. Little tea break. All right, so this doesn't help me a whole lot, but it gave me some insights, but it's not the whole idea. What I want to do now, and I'm going to do a little cleanup here. What I want to do is, oh, I should left. I'm going to leave those red things because that's going to help with the arrows. Just at least as a sanity check on things. I need more data. So now I'm definitely going to want to get some more points in here to understand what the general flow is. And you can kind of wing this. All you really care about is the sign, SIGN, of the X dot and the Y dot. So check out that dot that I just put there on the graph. Let me make it a little bigger. It's at, I'm thinking like 1 negative a half right here. And when I have 1 negative a half and I plug that into the system, I'm going to get X dot is positive and Y dot is also positive. But I already knew that, right? That's right here. But this helps me if I'm trying to make a sketch, this helps me get a little more accuracy. So that's 1 over and half down, or 2 over and 1 down. All I really care is about that general ratio. So what's a good color for this? I'll just do gray. So it's 1 over 2 down. Is that right? 0, 1 half. Let me check. It's no, it's it's over 1, up 1. What was I thinking? Don't screw this up again, bro. So at the point 1, 1 half, I've got X dot equals, I think I did some weird stuff there. I've got X. Maybe I did say all that, and I didn't say the slope right. So we've got X dot equals 3 halves, and we've got Y dot equals 1 half. So that's actually a ratio of 3 to the right, 1 down. So 1 up. So we go over 1, 2, 3, and up. So something like that. And then I just kind of wing what that would look like here. Let's grab a few more. So we didn't actually do this one at 1, 0. And you might want to even make a little table. So here's your point. Here's your X dot, here's a Y dot, if just to organize the information. So at 1, 0, we've got the arrow. I think we already did this guy and I erased him. That's 1, 1. So I've got a flow that's perfectly diagonal there. Now let's check this out because this guy down here that I drew first, I don't know, I'm a little concerned about that slope. So I'm just gonna pick a point just a little further down toward that line. So I'm going to take the point 1 and oh, yeah, I totally did that ass backwards. Dang it. Dang it. Sorry. I gotta stop this. No, I'll just keep going. Oh, fuck. We're too far in. I can't stop. Oh, well. Okay. Too bad. So this point, I'm writing the point coordinate wrong. That's 1 negative a half. Okay, this is way better. So X dot at the point 1 negative a half, we're going to have X dot is X plus Y, so that's a half. Y dot is X minus 1 half, and that is 3 halves. So it's the flip, which makes more sense when you look at the picture. That vector just didn't look right. So this means it's 1 over and 3 up. It's a very steep flow. And when you look at this, yay, that actually makes some sense now. Can we kind of think a little bit about what's going to happen as we move up? And we knew that this guy was 1, 1 here. Yeah, why not? Let's just move to green arrows. They're a little easier to see. You can see the slope flattening out as we move up. And as you approach that blue null line, you're going to get flatter and flatter slopes. Starting to manifest the current just a little bit better. As you approach that bottom null line, the slopes are going to get steeper. So if I'm way close to it here, I've got a very steep slope because these arrows move continuously. That's the thing to keep in mind. That's what was tipping me off that I was doing something weird. Luckily, pulled out of it quite well. Okay, so in this lower region, we basically got the flow defined by those null lines. We've got a flow to the left and a flow that is upward on the right. So the blue arrows are to the left, the green arrows are to the right. That means as I move from the green line to the left toward the blue line, things are going to flatten out. And it's probably the least effort route. They're going to fold over and to the left, but we could just check that out. Why not just be safe after, all the trouble and pain we've been through? So at 0 minus 1, we've got x plus y is minus 1. We've got x minus y is positive 1. So that is 1 over and 1 up, which makes total sense. We're about halfway on this journey from left to right, and the slope is straight up on the right side and horizontal on the left. And so we're just smack dab in the middle, the vertical average of those two. Get rid of those dots. And the same thing is going to happen as I move closer to this, the arrows are going to flatten out. As I get closer to this, the arrows are going to get more vertical. Doesn't this make more sense? As I actually approach 0, the arrows are going to shrink. As I get further away from 0, they're going to grow in magnitude. And knowing this now, I can wing it a little bit better, right? This one's going to be a little steeper than the perfect diagonal, and this one's going to be even steeper still. And don't worry about getting the magnitude. It would be helpful if when we do some sort of numerical method, and we'll talk about that. But really what you want is the quality of the flow for these portraits. Let's see if we can just wing this one here. Now we knew that x dot is negative and y dot is negative, so all the flow is going to be down and to the left. And right here, I'm going to take the average of those flows on the null line. You son of a gun. And as I get closer to the top ones, that's going to flatten out. As I get closer to the bottom ones, that's going to, as I get closer to the top ones, it's going to get more vertical. As I get closer to the bottom ones, it's going to get more horizontal. And then you see that you get a perfect -1 slope right along that whole negative x-axis. Yay. And then here we've got x dot is positive, y dot is negative. How much you want to bet? If we checked, we'd see that slope there. And then we'd see a mellower slope as we move to the right and a steeper slope as we move to the left. And now we've got a pretty good method. Remember, that one's going to be more horizontal. Do these diagonal ones first. That. Getting chill, getting crazy. I'm going to erase that now. Over here, as I move this way, things are getting steeper as they approach the purely vertical. See, and then it gets hard. Like just large slopes are really hard to make, and it's very small slopes. Could you draw the difference between? Those arrows are backwards. They should be to the right. Could you draw the difference between 1/10 and 1/20? I couldn't. Those guys are probably not steep enough there. There we go. Bob Ross voice here. Pretty little arrows. There we go. Check it out. Feel in the flow. And so now I can come in here. I'm going to come in with red and sketch some potential trajectories. As you cross a null line, you will always cross either purely horizontally or vertically as your tangent. So these guys, I hate that this thing does what it just did. It snaps me in straight lines if I go too slow, so I'm just going to try to go fast. These are the tangent vectors, the velocity vectors for your curves. And remember, they don't intersect. I'm going to add arrows to them. And now we have a phase portrait. Check out that equilibrium. Whoa, bro. Coming in the wrong way. Check out that equilibrium. Let's think about approaching it. So let's say I aimed for that equilibrium. And there's one line that heads toward it, and that's called the stable manifold. And there's one on each side here, probably. So I could find, if I got it just perfect, a line that headed toward that equilibrium, and there's going to be one of these on each side. That is the stable manifold for the system. Stable manifold. Because once I'm on it, I stay on it. It's a route, and it takes me to an equilibrium value. And I think I said that wrong the other day. So please note the difference here between what I'm saying. There's also one that if you bump over out of the equilibrium just a little, you'll head on this route. There's a route that seems like it connects. You can never enter an equilibrium and you can never leave it. But if you're close to it or you're close to one of these routes, you will head toward it or away from it. But you still can't enter or leave it once you're in it. And stable manifolds we got going on there. So that equilibrium is actually really weird. It's called a saddle point because it is both stable and unstable. So it's a saddle point equilibrium. You can see that if you tried to approach it, let's say we scooted just a little to the side of that equilibrium, I'd get swooped away and then pushed away. So notice how I'm pulled toward it. So there's some kind of stability, but then I'm shoved away and there's instability. And I would just fill in the phase plane with some more trajectories here. Despite a few almost slip-ups or slip-ups that were caught early, we've got a really sweet plot. And that, my friends, should get you going. Let me just get you the homework assignment. And we'll talk more about this on Monday. Please start on these because this is a challenging thing. It's a new thing. So the first problem, I'd like you to write these up. Like I said earlier, let's shoot for Wednesday to hand these in, but it'll probably end up being Friday because isn't it always? So please go through that step-by-step process and work these through. There is a D field plotter in the resources in the content area. If you go there, look for the one that's got Bluffington in the URL. I don't know how many, I think there's only one there and we discussed this, but use that one, switch the tab to system. You can enter these and check yourself. Click on the graph to get the plot to get some trajectories and see if you got it right. But you have to do this by hand. So this will be on the next exam, right? So let's practice it now. This and then this one, which is a slight perturbation of that, where we're just going to, oh, this should have been in, yep, that's right. Yep, that's all good. Everything was fine with that first one. And then this is negative, and this is y dot equals negative x plus y. So notice all that changed was the coefficient on the x in the x equation. And give it a shot. See what you get. What happens? How do they change by making that change? What does that do to the system? What does that do to any equilibria that appear? Here's a little hint. Your only equilibria here will be 0, 0. I think on Monday we're going to do an example where there's multiple equilibria. Really cool example. And then we can do some relationship stuff. But please write up, and I would like you to show these steps. Please show steps. You know, 1, like I said, null clines. 2, what is the equilibrium? And show the work for those. Show the work for finding those. Step 3 is, you know, sketch the flow, sketch the arrows in the phase plane. And then step 4 is sketch some trajectories. This all has to be done by hand, but totally check yourself on these plots on the plotting app. All right, my friends, I hope you are having a good snowy day, and I will see you on Monday. Bye-bye. Gonna probably take me a second to hit stop here. Okay, stopping the share. Now I'm ending this. Bye-bye.